just keep them coming in. All right, I don't see too many coming past my eyes from my group, so keep them coming in. Remember, you may need that extra little push over, all right? So it's called B4, it's probability 1. Now, in your books on page 135, it just gives you a little idea about, you know, why probability came about. All right, I guess it's got to do with the gamblers in the world. Can never get rid of them. But for our generation, all right, today probability has many commercial and scientific applications. You'll be amazed. That's why they keep all the data on you, you know, about life insurance companies and what they're willing to, I guess, put towards you, depending on certain things that they know. Car and property insurance, again, the likelihood of a flood, right? They think about that. It used to be said in Newcastle, it used to be called the 1 in 100 year flood, and when we built our place and we heard them say, you know, you had to build up higher because it's a 1 in 100 year flood, and we'd say, when is it ever going to flood in Newcastle? When do you think? Well, if you were all around in those years, I think it was it 211? No, 207 I think was the big one, wasn't it? Do you remember? You're not that young, are you? That you can't remember, you know, the Pashabolka? You're not that young. So Pashabolka was, I think, in 2007, and sure enough, our place flooded, so they do get it right, that sort of thing. Share trading, medical considerations. So all of these things do play a part in your life, even though you don't realise it. It's going to be part of your life. The important idea about randomness, and again, you'll see them, the questions are stated such that it says a student is selected at random, and people never know what that means. And it's just saying that suppose 5 different name cards are placed in a hat and one name is drawn at random. This means that each name is equally likely. So that's the thing you don't see in the actual questions. You don't see them point that out, all right? But your job's to say that that would have an equal chance. The 5 pieces of paper in that hat have got an equal chance of being drawn, and that it is not possible to predict which name would be drawn, okay? So equally likely becomes an important little phrase for us. Then it says, now suppose that 5 students are involved in a running race. Is each student equally likely to win? What would you say? What do you reckon, Jayden? Was that a shake of the head? All right, why not? Probably because there's some talent, I would imagine, or some ability, all right? Or lack thereof. Yes, if I was one of the members of that race, or lack thereof. So it's getting you to think about that, all right? So on page 135, there's a lot of definitions. You've probably heard them before, but it'll say things like, an experiment is any situation where the outcome is uncertain. You don't know what could happen. Random variation is when it is impossible to predict with certainty. Really and truly, this could happen, but it may not. All right, for the certainty with the exact outcome of an individual experiment. But as the experiment is repeated a large number of times, however, it says that a regular pattern emerges. So we can say things, if we did this experiment 1,000 times, then we think it'll happen so many times out of 1,000. We use the big P, the capital P, for probability. It's the measure of likelihood or chance of an event occurring. We talk about that event, all right, when it comes up. It could be the event of rain today or something like that. It might come up as a percentage. It might come up as a fraction. It can come up as a decimal. All 3 are legitimate. It does not matter which one you give us an answer in. You don't have to give me all 3. Make sure you know that, because that would just be time wasting. So it says an outcome is the result of an experiment or a game. Now here's the part that can sometimes confuse people. Outcomes are what might happen, what could come up. So for example, on the right hand side it says rolling a die. When you have a die, 6-sided die, the outcome, all right, might be for getting the 3, all right. Sample space, however, is the set of all the possible outcomes, and that's the thing that sometimes will hurt your brain. Not so much this time, but next week when you do probability part 2, all right, you are going to be forced to think about the sample space. What could it have been? Now with rolling a die, obviously there's 6 things that can happen. You can get a 1, a 2, a 3, a 4, a 5 or a 6. As the questions get harder next week, it's that sample space that you want to see, listing it down so you can actually see what could have happened. All right. E, the event, is a set of 1 or more of those outcomes, so it might get defined as find me the even numbers. So within that sample space, you'd look for the even numbers. Could be anything else, but the event changes. It depends on what the question wants. And mutually exclusive. You will see this a lot in statistics, and if you have to do a course next year that says you have to pick the stat course, you might investigate this mutually exclusive a little bit more. But for the moment it says there are events that cannot occur at the same time. So for example, if you're talking about rolling the die, you can't get a 3 as well as a 6. Alright? Now you might say a 3 and an odd number, they're things you can get at the same time, but the event of getting a 3 is mutually exclusive to the event of getting a 6. Okay? Successive events, again it's going to be part of our words today, are 2 or more events occurring in succession, asking you to find if you can get the 3, then pick the die up and roll it again, and then get a 4, so one followed by the other. Independent events are successive events when the occurrence of the first, what happens, alright, in the first one has no influence on the occurrence of the second. So whether you say, if I roll the 3 on the first roll, when I pick the die up and go again, did it matter what I just got? No, it did not matter what you just got. Okay? And if it's non-independent, so this is the difference, okay, the first one is independent, doesn't matter what happens on the first roll when you go to do the second. However, non-independent, there is going to be an effect, and it says, for example, 3 red marbles, 3 green marbles in a bag. You pick 2 marbles, first of all, okay, you pick the first marble and you're holding it in your hand. Do you think that the first event affects the probability of the second? It does, because whatever you're holding in your hand has changed the possibles in the bag. Alright, so these are non-independent, okay? So for example, just like the little animation has there. So you guys are now on your page, pretty straightforward, page 136. The notation says the probability for a simple event is n of e, so this definition down here says just count out how many elements are in the event. The event is what the question has asked you for. If it's talking about that die, it might say the event is even numbers. How many evens are there in the actual sample space? So n of s is always the sample space. That's why this has to be locked in. Next week this gets harder because the sample space grows significantly. So this is the idea. Whenever you do a question you're not sure about, always see if you can break it down. Any hard question, think about what the sample space is. That becomes your denominator. So your sample space is on the bottom, however many there are in that sample space. And then at least think about the top. It has to be a number lower than that number. It can be a 0. It could be a 0 sitting on the top. Could be a number smaller than the n of s, or it could be exactly the same. Can it be bigger than the n of s? Can it be a number bigger than the number of elements in the sample space? Can it be bigger on top? Should not be. Yet we will still get people who put fractions in front of us that are bigger than 1. If you get an answer in probability where your answer is bigger than 1, it means you've made a mistake on the count somewhere, because you are only going to be limited between 2 certain numbers, and people don't stop and think they may just have done a slight mistake in their counting. But be aware of what you place on top and what you place on the bottom. So here we go, pretty straightforward. This is done in your book. What's the probability of obtaining an even number? That there is the event for our question. When a die is tossed once, so basically you think about the sample space and you can write it out. You think about the event, which was how many of them are even. Okay, 2, 4, 6, so there's 3. So what that means is you've got n of s is 6. There's 6 elements in there. There's 3 elements in this one. So the probability will be 3 on 6, which turns out to be a half. Okay, so keep thinking very simple probability. Break it all down. Range of probability, it says, goes from 0 to 1. So you know that if it's 0, it means it's impossible. And you might get asked to name something that is an impossible event. So stop and think about that rather than just always doing the calculations. Can you put an example to something that's impossible? Our fractions go from 0 to all the way to 1, so you know that the closer you get to 1, the better your chances are becoming. And if you are exactly 1, it means the event is certain to occur. Again, people might get asked, and this is what throws people, to think of an event that is certain to happen. All right, so be aware that, you know, they might throw something like that at you in an exam. This one here just says, you guys have got the space down there, it says what's the probability of obtaining a multiple of 3 when a die is rolled? All right, is rolled once. So here we go. Sample space. Again, make it really obvious, because if you can do the setup for an easy one, then you can do the setup for the harder ones. Okay, remember, next week gets a lot harder. Okay. Sample space is that. The event, in this case, I'll put the event is, all right, a multiple of 3. So which ones are multiples of 3? So again, even in this probability question, you might get thrown because you can't remember your factors and your multiples. Multiples should be starting at 3 and getting bigger, so the only 2 that come up are those 2. And it said the probability of getting a multiple of 3 should have been n of e. Now I'm doing this because next week when things start to get harder, you just fall back on this simple idea. Count how many ways the event can happen, which is 2. Count how many ways the actual sample space has in it, how many elements, it's 6. So it becomes a 1 on 3. Alright, so if you're not sure about the notation, this is n of e, which is 2. This gives you n of s, which is 6. Now you might say, well, it's pretty straightforward, I could do that without all the working. When I start marking the class that I have, the tutorial that I have, the group of people I have, what I'm also looking for is how you communicate your maths. You might have the right answer sitting on that page, but a lot of you are shocking at your working out. Now, this is not kindergarten anymore. You are about to go into uni, hopefully, fingers crossed, you get into your courses. And you've better start figuring out that it's not good enough to be sloppy. It's like sentences that just have half of it missing. So please make sure you get used to labelling what you're doing. That's just like a common courtesy of how to write mathematics. Here we go. It says a bag contains 7 red balls, 6 blue ones and 12 white ones. If one ball is taken at random out of the bag, find the probability of getting, and then it says a white ball and then it says a red or a blue. So first of all, I'll say n of s. I'm not going to write them out because it would involve, I guess, writing red 7 times. Well, I don't plan on writing that 7 times, and these b's, all right, 6 times, and these w's 12 times. What I am interested in is the n of s. How many are in the sample space? Anyone tell me? 25. Add the 7 and the 6 and the 12, and you will get yourself your 25. So there is 25 in the sample space. So I expect to see a 25 in the working. So it says the probability of getting a white ball. Now what you can do as well is just say this is the event. If you want to put the word down so you can see the event. Alright, the event that is happening. So n of e is going to be how many white balls? There are 12. So the probability becomes a 12 on a 25. Now I tend to always show my original numbers before I simplify. So I'm always saying to the person marking my paper, I might go wrong in the simplifying, so I'm actually going to show you where I started and then what else happened. No, there's 25 to pick from though. Why would it be 24, Nicholas? There's 20. You might have. Yeah. So round 1 we haven't taken it. It's coming though. Yeah. So the second one says, now this says a red or a blue. So think about what the event is in this particular case. So what's the number in the event? Well, it says it can be red or it can be blue. So that means it's going to be 7, or there are 6 of these. So there's 13 ways this can happen. So the probability that it could be red or that it could be blue is equal to a 13 on a 25. And I was about to say before, I always show my original numbers, and if anything simplifies, that's great, but if it doesn't, all right, then leave it there. Please don't go into a decimal. It's just a bit of a waste of time as well. So I just tend to say you should just be able to walk away from that question. How about this one? I have 25 white balls and 40 black in a bag. What is the probability of randomly selecting a black ball? So think about the N of S and think about the event that's going to happen. I might just actually put that underneath. I might put that one underneath like that so I get the first number. How many ways can you get the event of having a black ball come out, which is 40? How many in the sample space? 25 white and 40, which means there are 65. So what would be the probability of getting a black ball? So it should be probability of getting a black will be 40 over 65. That's my original number. I don't see it there, but 40 over 65 looks like it might go to. Any suggestions? Eight over 13. So an 8 over 13, all right, which would be, all right, one of those. An 8 over 13. I think I have to tell Mr. Dave. Don't tell him, but I think he's wrong, Justin. We'll have to counsel him about that. I'll have to counsel him before I bring that up with him. Adam, Ben, Chris and Dan run a 100-metre race. What is the probability that Adam wins? Now this is one of those we prompted you before about, do you think that these are all equally likely? So I'm going to put, you know, are they all equally likely? So don't go for the obvious, I guess, which was, it looks like a 1 on 4, I guess, because it's actually going to need a bit more information, because there is, as again, some skill or lack of that comes into play in that. All right. Now cards. Now we may not be card lovers. That's okay because we put it up in front of you. If you want to jot some things down, we tend not to put too many of these in our quizzes because we understand that not everybody knows cards. All right. So what it's going to have come up, just a couple of descriptions. If you didn't know, if you've never played with these cards, then the Jack, the Queen and the King are called picture cards. So highlight that on your page 137. If you've never seen or played with these cards, picture cards obviously have a picture. Sometimes people wonder about the ace, but the ace doesn't actually have a picture, so in our definition it's not one of the picture cards. It also says numbered cards. Obviously the 2, 3, 4, 5, 6, 7, 8, 9, 10, they've obviously got numbers. So the ace sort of sits out on its own. It's not a number and it's not a picture. Each of these suits, we call them, we've got 13 cards, so 4 13s make 52. So there are 52 cards in front of you. It's called hearts and diamonds, which are red, and you can't quite see that in your book, it's not printed. So if you're new to this, the top 2 are red, and the bottom 2 are called clubs and spades. Now just a little bit of that idea to get us through all this, and it says here, resource sheet suggestion. You might not want to draw it all up, but if you want to just put something simple on there to remind you about what's a picture card and what's a numbered card. So here we go. A card is drawn at random from a pack of 52. Okay, 52 is what's called a standard pack. It doesn't have those jokers involved. What's the probability that it is A? Now you've got, I think there's 8 questions coming up, and this PowerPoint keeps these cards on the screen for you. So hearts, there should be 13 of them, so I'll put there for the probability of a heart should be 13 out of 52, and then that would simplify, okay, to a quarter. That's round 1. Round 2 says a king. Probability of a king, again it's out of 52 because that's the sample space. How many kings are there? There are 4, so that should come down to 1 on 13. This time it says the probability of a heart or a king. Probability of a heart or a king. So out of 52, you've got the grid in front of you. Count up. If you're a heart, that's 13. Now if you're a king, you might say, can I put the 13 plus the 4? But if you did the 13 plus the 4, what's the problem with that? You've double counted, and that's going to be the slight hiccup. So if you've got it in front of you, you can actually count them out. But otherwise, if you go, and I'll write it down, but be warned, I don't want to see a 13 plus a 4. There's caution there, unless you take one away. So you might see that in people's working. Me personally, I probably wouldn't have counted it twice, but be aware that if there's people that just take 13 hearts and 4 kings, you're going to get it wrong. So it should have been a 16 out of 52. And then a 16 out of 52, what goes into it? 4s. 4 goes into that, and 4 goes into that one. And again, 4 on 13 probably doesn't come out to be a nice decimal. I wouldn't even bother going with a decimal whatsoever. Okay? A heart and a king. Now there's a change, and that's what's going to be bothering us more so in this particular topic is the words, or are the words, heart and a king. So, out of 52, how many can I count that are a heart and a king? Just one. Just one, and that is the King of Hearts. Alright, so being careful to watch the words. An and can make it a very different answer to an or. A Queen of Diamonds. So again, probability of the Queen of Diamonds. How many are there out of 52? There's only one. A red card. Probability that it's a red card. Again, out of 52, I'll go and do the right thing and put 26. But you can see that that comes down to a half. And then it says a picture card. So keeping in mind which ones are picture cards, out of the 52, alright, there are 3 in each suit. So you might say there's 3 in every suit. So that's a 12 out of 52. And again, do a bit of a division. Divide by 4s. I think we'll get a 3 on a 13. Keep an eye on just my simplifying as well, anybody. 3 on a 13. This time it says a picture card or a spade. So again, start counting them up. They have to be the pictures. Or they can come from the spades, one of the black groups. Out of 52, again, picture cards. There were 3 by 4, which is 12. You might say there are 13 spades, which is the bottom row, okay? But you will have double counted this and this and this if you did it that way. So again, just being careful to adjust. You can either just be someone who counts them out, or you can put them together and subtract the one you counted twice. So 13, I'm going to put there's 13 from the spades, and then there's another 9, which gives me a 22 out of 52. Looks like 2's going to go into both, 2 into that, and 2 into that, I'd say. Righto. Then we've got a number from 1 to 20. Sorry, the numbers from 1 to 20 are written on 20 cards. Alright, imagine that they're put into a hat. A card is chosen at random. So straight away I've got up here that the sample space has 20. And now I have to make sure I can pay attention to the words. So it's got, the first one is if it's a multiple, alright, of 5. A multiple of 5, how many out of the 20 do I think are multiples of 5? So I'm going to put, what's the event for this one? It's 5, then it's 10 and 15 and 20. So how many are there? So it would be 4. So that's a 1 on 5. So I'm going to do that each time. I'm just going to write the event and what's in the event if I can. Now you'll be amazed at some of the mistakes you probably make. Even though you think this is simple probability, which it is, if sometimes you take sort of that rushed effect happens and you say, I think I know this, I can see it in my head, sometimes you do miss out on things. So here we go. The probability that it's an even number. And again, I'm going to say it's out of 20. I'm going to look for my event, which is even. I'll write the numbers 2, 4, 6, 8, 10, 12, 14, 16, 18, and a 20. So it looks like there's 10, which makes it a half. What's the probability that it's odd? Okay. Again, first of all, I'm putting my over 20, so it's ready to go. Because even if I get pulled up, I've written something down, maybe I'll get some marks for it. Alright, all the odd, I won't write them out, but I can see there the other 10, which gives me a half. Contains the digit 7. So it's just got to have the digit 7 in it. Contains, I'll just put that there, contains the 7. How many do you think? Well, I'll put the event up here. I think my brain has checked off the 7. and it's checked off the 17. So I think there's 2 ways that can happen. Contains the digit 2. So here we go again. Contains the 2. Let's think about it. Out of 20, the event could be, I'm thinking of the 2, the 12, and the 20. Can't see any other number at the moment, so I think it's a 3 out of 20. Contains the digit 1, so again I'll put the event down here. There's the 1. There is the 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. How many have we got in that particular group? How many out of 20? Anyone else get 11? Anyone else get 11? Doesn't simplify, so we're away. That's it. Bit about expectation. Okay, this is as it sounds like. It sounds like this is what we expect to happen. It doesn't always, but in theory, this is what we say is what I'm assuming might happen to us. So it says, for example, you might do 500 trials of an experiment, which is throwing the 1 die. What's the expected number of times that a 6 will be uppermost on the die? Now, I've got another group that I teach, and they don't like the word uppermost. Why do we have to say that? Well, I think it's just clearing up that we're talking about the face on top. I know you'd say, well, wouldn't that be the obvious? I know that's the obvious, but other times people have other ideas. So you'll see that word uppermost. It's just saying the face that comes from the top. Probability of a 6 would be 1 out of 6. So the expected number would be 500 times 1 on 6. If it comes out to be a number that's not an integer, for example 83 1/3, then you decide to round that down to say it's 83. Now there's a couple of other examples up here that are not in the book, I'm pretty sure. So this says on page 138, it just says if little p is the probability of the occurrence of an event in a single trial, then what happens is the expected number of occurrences, or its expectation that the event in n trials is defined as. Now this is just an event, the expectation, sorry, is the little n times by the little p. So in case you've forgotten, there's a multiplication in there. How many times are you doing the trials multiplied by its probability, okay, of that event? This is the number of trials, number of times you repeat yourself. Alright, so then it comes up with a spinner there, and it's got lovely colours up here, red, green, yellow and blue. 75 spins of the spinner. What's the expected number of times that it will land on the red? So the expected value would be n times p. I'm doing this experiment 75 times. The probability of getting the red, it looks like these are all equally likely. So that means that they would all be a quarter. So 75 times a quarter. Tell us what you get for that besides 75 on 4. What kind of number does it come out to be? Is it a integer? I don't think it is an integer. What's it come out to give us? 75 divided by 4, 18.75. How many times would you expect it? We're usually given a whole number answer. Which one will we give? 18 or 19? Therefore, expect 19 times. We're expecting it to land on there 19 times. Okay? But what we expect and what really happens can be two different things. But that's what we're sitting here right now thinking about the future, and I expect it to happen 19 times. Okay? So it'll go through, do all that, done. In 90 spins of the spinner, which is your question underneath, what's the expected number of times that it will land on red? And again, same thing, keeping in mind that the expected number will be 90 times by a quarter. And again, you get 22.5. Now, at that point, all right, you could say it might be a 22 or a 23. So we actually accept both in that case. All right. Complementary events. This is going to be crucial to us because once you know about probability trees, which many of you know about, probability trees. Probability trees only work if you know about complementary events. So we've got to first of all make sure that everyone's got this groundwork pretty stable in their mind. So it says we've looked at the probability of an event occurring, and we'll now look at the probability of an event not occurring. So you might say, why would I need to know that? Well, there's something that you should know about these probabilities. It's given a name. It's called its complementary event. So, for example, the complement of event E is the set of outcomes that are not in E. We tend to write them like this. This is the E, and then the complement has a bar over it. It can sometimes have a wavy one as well. So if you're looking up any textbooks or any websites, all right, and you see that bar on the top, it means not in whatever's sitting underneath it. So this says whatever is not in E, whatever is not in the event, okay? So the sum of the probabilities, it tells you, okay, of these two complementary events has to be 1. So it says here, setting it up, the probability of the event plus the probability of not the event happening has to equal 1. So then it just puts it into like an algebraic form. And to make it even simpler, the probability of a complementary, that's what this is. This is its complement. This is its complement, will be 1 minus the probability of the event occurring. So making sure your fractions add up to 1, making sure your decimals add up to 1, making sure your percentages add up to 1 when the questions come in your way. This is page 139. It says find the probability of obtaining anything but a 3 when a die is thrown. So you're going to say, well, what I need here is a complement to come into action. If I know that the probability of a 3, all right, is a 1 out of 6, so not being a 3 will be its complement, okay? So that was already written down for you guys sitting up there. Now we're up to the one that you have to perhaps, no, not fill in, just a big gap. The set of cards are numbered from 1 to 23, so I will put down here that the N of S is 23, just so we remember that it's out of 23. One card is selected at random. What's the probability that the number on the card is divisible by 3? So this is the event we're thinking about. How many of them are in the event? Because then I'm going to ask the not divisible by. So it's much easier just to think about what if it was divisible by 5. So you think about the numbers, 5, 10, 15 and 20. So there are 4 of them. 4 out of 23 would give you the event. So the complement will be 1 minus 4 out of 23, which saves you from having to count things. That's also the advantage of a complement. Alrighty, so we're on page 140. Now you may not prefer Venn diagrams. They may not be your choice of how to get through a question. You might say, can I get through a question another way? That's fine, but if a question gives you 2 marks for your Venn diagram, then you better learn to draw Venn diagrams. If you had a question come your way that did not set you up, that said, do this any way you like, then you've given a choice. But if there is a Venn diagram and the question says, I'll give you 2 marks for that diagram, then you've got to sort of understand how to draw it and how to get things out of it, how to get information out of it. So here's some basics. As I said, this is probably something, if you ever did it, it would have been a long time ago. It doesn't really come back up in many people's maths sort of lives. So this is the terminology. A set is any collection of objects specified in a certain way. Capital letters are often used to designate the sets. Lowercase letters are usually used to describe the elements. So these are the ones that go inside the set if needed. So it says the main things are, we use a capital U. That's the universal set. The universal set is always how many people did you start with, how many bits of data did you start with. So this is going to be the crucial part, this one here. The complement of A. So you can see these diagrams that go along with yours as well. You can see that if in the circle is the event A, then not A is outside the circle but still within the universal set. So please make sure you have a universal set, because otherwise you are not confining yourselves. Universal set says this is what I've started with. Otherwise it seems to be undefined, therefore it would have no limit. Now this is a different sort of U. This is a union. Okay, so that's not a letter, capital letter U. That symbol there says this is the union. So this is all the elements that are in set A as well as set B. Now you'll notice that it's all coloured in, even the overlap. So when I said before if it was a spade and a picture card, alright, so you counted up anything that was in the spade as well as was a picture card. This is not an N, but it sort of looks like an N, so it's the intersection. And in words, this is usually when we say if you're a member of A as well as being a member of B. Okay, so then you can see where it pops up in the Venn diagram. It's also got on the right hand side of your page, it's got probability of an A and a B. So you can see here, if you are in set A and set B, this is like the intersection. So it's got it highlighted there. The probability of an A or a B, so the words are going to be the killer in this particular week, alright, is when you put A union B, alright, so this is the union. And then what tends to happen is when the words say the probability that you are A or B, or it might have said A or B only, so they didn't want you to be in the overlap. Alright, so they didn't count the ones in the overlap. They only had A, they were an element of A, or they were an element of B, but they weren't in the overlap. Okay? And another little sort of thought when you're coming up with your own Venn diagrams, there are two ways you can draw it. It says you can either show the raw data. So showing the raw data takes more time, because obviously if you want to talk about letters of the alphabet, say up to a certain letter, you can see you can put the A, B, C, D, E, F, G, H, I, J, K, L, M. You can actually put every single element, and they're using small letters for that. Or you can just put the number of data. So that means I think there are 3 elements here. I think there is 1 element here. There are 4 elements in here, and there are 5 on the outside. And together, I would be able to tell you this is faster, the bottom one, because the bottom one says I can count that I've got 13 in the union. So 13, that would be in the, sorry, universal, not union. 13, that's in the universal, which is faster than having to count up all those letters up there. So there's 2 ways. So when you go to draw it, it's up to you if you find it easier just to put them in individually or just count them. How many elements are in the following set? So from the top of page 141, okay, your job is to answer these questions. There's a whole string, it's on the top of page 141. Your job is to say how many elements are in A. So if you're new to this, put your finger around A, go right around the circle, count how many you should have in there. Alright, call out for A. How many have we got for that one? How many have we got for A? 40, so I'm going to put 35 plus 5, which is 40. Okay? So for B, let me just see where these are going so I can just remember where to write them. So I'll move this guy out of the road for a second and just put it under here. This was a 35 plus a 5, which is a 40. How many elements are in B? So how many elements are in B? The answer would be a 20 plus a 5, which is a 25. A union B. How many in that? Anyone want to call out an answer? 60. So the elements that are in A union B, I can see I've got a 35 and a 5 as well as a 20, and it gives us a 60. A intersect, so I'm saying how many are in this set. A intersect, that's an intersection sign there. How many are in that group? There are only 5. Same question, you guys have still got some more space, so I'll just get all 4 of them up on the screen there. So this says not B. So put your finger over the circle B if you can, anything that's in the B circle. How many can you see that you haven't covered, I guess, or are still poking through? What can you see? Any ideas? I'm seeing a 35 still pop up, and I'm seeing a 40, so I'm seeing a 75. So remember, think about where the B is. Alright, that's these guys here, and you want to say not those guys. So I tend to just cover it up with my finger and then I just see what else is still poking out. Now you remember what we said? A intersect B. A intersect B was that one there. Okay? A intersect was that. So what's not? How many would you say are in the not? Count them up. How many was it? 95. So the not. So again, I'll say what I did was I looked at what was underneath the bar, A intersect B, and I've sort of put a little colouring in on it for 5. Well, I don't want that. I want everything else. So I get a 60, sorry, I'll get a 40. I'll put it down as individuals, and a 35, which gets me a 95. Now I'll cut that coloured in bit out. A union B. So find what A union B looked like. This was A union B before. That was A union B. Now I'll say not. Who's not included? How many are there? 40. A union B and then a not, and it's going to be 40. Now I'll get rid of all those marks there. Now watch carefully. The bar is only on the not A. So first of all I'll show you what A is. So here's my A. Alright, and it said, I want how many are in the not A. So can you see what you're looking at? You're looking at these guys and these guys. And then it says I want you to intersect with B. How many have I got? I've got 2 things ticked. Do I want both of them to be counted? Any idea on a total, on a number? Any thoughts? What do you reckon, Rebecca? Well, it says not A, so there's 60 so far. So there's these 60 I'm staring at, and then I'm being asked, out of those 60, I want to intersect with B. So that would be just those 20 in there. Just those 20 in there. A bar, and then intersect with B. So again, a little bit of a diagram, doesn't have to take up much, but it might end up helping you through those tighter ones. Okay? So here we go, a bit of a diagram. This has already been drawn. You can see 2 versions. One's got the raw data and one's just got the number, okay, of data in each particular set. A set of cards numbered from 1 to 20 is placed in a box, and 1 card is drawn at random. Determine the probability of this card being, and it goes through a couple, an even number, a multiple of 5, and then it's going to ask an even number and or a multiple of 5. So obviously the sets, before I start drawing my Venn diagram, I tend to listen to the question because that's going to make a decision on what they want me to draw. It's got an E for even, it's got an M for a multiple. Now it's going to present the first diagram you've got, so I'll just tap away here for a while because all the numbers appear as you go through, depending on whether they are even, multiple of 5, or both. Now that's the raw data diagram that you've got, and now it's just going to tell me how many were in each particular position. So it's counted them up, so it's telling me how many I found in each zone. So first of all, number that we thought was even in the E set, and again, put your finger around the circle. Okay, you should have an 8 and a 2, which gives you a 10. That's why it becomes 10 out of 20. Multiple of 5, you can see you should have circled, or you're counting the one on the raw data. But you can see the 2 and the 2, which makes there are 4 elements. So it's 4 out of 20, which gets simplified. And it's the last one, if anything, that's going to trick anybody. It's an even number and a multiple of 5 or a multiple of 5. So it's about who do you want to count. So you're going to count the 8 that are here, the 2 that are here, and the 2 that are here. So an even number and a multiple of 5, or an even number or a multiple of 5. All of those got counted in. Now there's one for you to do. Okay, there is one for you to do. So grab a pencil. My suggestion is always grab a pencil. Are you going to put, well, when I say raw data, I don't want to name the 30 students in this class. All right, but I'll just go with not the raw data, but I'll go with the number of data. Now, probability questions like this, all right, come to you in different ways. When it's a Venn diagram question, they can give you different clues. So we'll set this one up and we'll listen out for the clues. There are 30 students in an English class. Now, the first thing I tend to do is put 30 down here, because by the end, I'm to have 30, not more than 30, not less than 30, but exactly 30. Of these, 19 study biology, so I'm going to put a 19 on the biology. 13 study physics, so I'll put a 13 over on the physics. And 5 study neither. Where do those 5 go? Where do those 5 that study neither go? Sounds good. Not in a circle at all. So I have them floating anywhere but in a circle. Now straight away I've put those numbers down, but I obviously have a problem. I listened to the clues, I heard all the numbers. What's the problem though? What can you see is the problem? A 5 and a 19 and a 13 make more than 30, that's for sure. So add them up and say I have a bit of a problem. So you've got your 5 and your 19 and your 13. All right? Now you obviously know there's a problem in there. So what I tend to do is this. These guys are fixed. These 5 here, no doubt about it. There's nothing that could have gone wrong with them. So I'm just going to say the 30 take away the 5 that were neither, leaves me with 25 students who should be doing, biology, physics or both, right? But I can already see, and I'll put a little exclamation mark here, but I can already see that 19 and 13 make more than 25. So 19 and 13 have already added up to 32. So I have a problem. There are only 25 students that should be in those circles, but I'm giving myself 32 to squeeze in. What's it mean in simple words? Yeah? What do you reckon, Brendan? You've got a number that are doing both subjects. But did I hear you say what number? Oh, how many are doing both? Why'd you say 2 though? Why'd you say 2 students? Is that what you mean, Brendan? Well, it's not 2 because I've got 32, but 25 should be doing bio or physics. You're looking at 30 as a whole, right? But we've already got 5 that we've already decided, put them on the side. They're the ones that aren't doing any subject. So I would say it's a 32, take away a 25, which leaves me with 7. Now what you do is with your pencil, you put the 7 in the middle because they're the overlap. So the 7 mean you've picked 7, sorry, you've uncovered, that 7 are doing both bio and physics. Now, the thing is you have to adjust this one, so you bring it down by 7. You have to adjust this one, and you bring it down by 7. And the last thing you should do before you answer any of those questions up there is check if those numbers still add up. Now, I didn't rub out my 19 or my 13. I left it there because that's what I started with. So do a quick check. Do you still have 30 students completely? Not less, not more? Sounds like we're ready to go with the questions. Find the probability that one student chosen at random studies biology and physics. All right, so the probability of biology and physics should be something out of, and I'll put up here, something out of 30. How many have we got? Biology and physics, we counted 7 of them. Doesn't simplify. Second one says physics only, so being careful just to say this is physics only. So how many out of my 30 do physics only? Looks like there's a 6, and that comes down to a 1 on 5. Remember, always show your original because you might do some simple maths in your head badly. It says that do biology or, so probability that they do biology or they do physics. So out of 30, you say how many do biology? So I'll say 12 plus 7. How many do physics? Well, I'd love to say 7 and 6, but I've already counted those 7 in the middle. So how many do biology or physics? I'll put it up here as a 12 plus a 7 plus a 6. That's a? Yeah, because bio, hands up if you do bio. Some people have got one hand up. Hands up if you do physics. Other people put their hand up. There are some people with both hands up, but you don't double count them. They're not 2 people. Is that okay? That means I count the 12, the 7 and the 6. So I get a 25. And again, I've shown what I was doing. I didn't just come up with a 5 on 6. I don't tend to give a simplified answer. all right, and walk away. I tend to show people where it came from because I always think if I'm wrong, they might be able to give me some marks for it. What's the probability that they do either biology or physics, that they do bio or they do physics? Now that sounds like you're not counting the ones in the middle, all right? Those words seem to be saying go for just the bio group, go for just the physics group, all right? You do either bio or you do physics, but it doesn't sound like you're doing both. So I'll put here the word only bio or only physics. Out of 30, only bio there were 12, only physics there were 6, and again that's an 18 on a 30. Looks like it's going to be divided by 6s, 3 on 5, with that answer there. Now we're going to get ourselves to the end of the next page, 142, and then we'll have our quick break. So we'll get to the end of our Venn diagrams. Are you ready for round 2? Now the clues might come out differently, just depends how they're dealt to you each time. So there's a space up here, it hasn't got anything else there. Out of 40 students, now I tend to put my diagram, have my universal set. Not quite sure what I'll put in there yet, but I know that there are 40 students in that universal set. 14 are taking English, 29 are taking chemistry. So it sounds like we're talking about English as a subject, chemistry as a subject. If 5 students are in both classes, so that sounds like I've locked that in somewhere in my mind. I know where those 5 are going to go. Construct a Venn diagram. So it sounds like I've got a circle for English, sounds like I've got a circle for chemistry. It sounds like I've got 5 students are in both, so that sounds pretty obvious as to where they're going. Now it said 14 take English, so I'll put the 14 there, but we already put 5 of them in the circle. So there aren't 14 students over there, but how many? How many does it bring it down to? 9. Are there 14 doing English? Before you go anywhere, a 9 and a 5 make 14. Yeah, I've put my 14 in the English class. There are 29 who were doing chemistry, but I'd already placed 5 of them, so that's going to come down to 24. And before you walk away, you never walk away until you do a final check. Do a sum of the 9 and the 5 and the 24. How many do you get? How many do I get? 38. I'm getting 38, so what does that mean? We've got 38 so far, so there must have been another 2 floating around. Now most people would not bother completing that. They'd sort of just keep going. They wouldn't even stop because the question didn't say anything else. But you've got to make sure you've accounted for all 40 of them. What's the probability that a randomly chosen student from this group is taking only the chemistry class? Only the chemistry class. So the probability of chemistry, and I'll put only. How many have I got out of 40? Out of 40, I'm getting 24. And that probably simplifies. I'd say 6s, make it 8s. 8s probably go into that. And again, I didn't say it out loud, but every time I got an answer, I was checking whether it was between 0 and 1 every single time. Now you've got this ready to go. It's got 3. We don't tend to have too many that are 3 circles. So this has been given to you fairly simply. It hasn't been given to you with many words. It's only been given to you with symbols. It says complete a Venn diagram given the following. So can you see along the side you've got information about the universal, about A, about B, about C. Then it tells you A intersects B, tells you A intersects C, tells you B intersects C, and the last one tells you A intersects B intersects C. Alright, if you've got a pencil, start drawing. Let's make sure we've all got the same positions. I'm putting my A there, my B and my C. My A, my B and my C. Start filling in where you think you might want to start. And in the end, whatever you have, I will tell you that there are some that are not in A, B or C. So you should expect to be looking for some that are not in any of the circles. So have a look at the info. So anybody waiting to go, I'll start my thinking. This is the universal. So it's got 44 in the universal. I start with a 28 up in the A. It may change. I've got 20 in the B. It may change. And I've got 14 in the C. And I've got 14 in the C. Now I know I wouldn't stop there because I've got way more than 44. So the next clue says A intersects B, A intersects C, B intersects C. It depends if you want to work with that or the very last clue. A couple of ways of thinking about it. I'll go for the A intersect B intersect C. I know that there are 6 that are doing all 3. I call them subjects if you want to think of it like that, or sports. So that's that one dealt with. I'll go back to the A intersect B. The A intersect B should have been in this sort of zone here, A intersect B, and it wanted 10. Well, I've already got 6, so there must be another 4 there. Then what I do is I notice that I can do some adjusting. I'll do the adjusting at the end. That's round 1, so that's that one taken care of. I'll look at A intersects C, that's that one there, like a leaf. A intersects C, there should have been 11, but I can see 6 were already placed, so there must have been another 5 sitting there. And B intersects C is like this bottom leaf down here. It says there should have been 8 overlapping, so I was missing 2. Now I had those original 3 numbers, they have to change. Alright, so where C has 14, I've already got 5 and 6 and 2, so I've already got 13 of them. So this number here is going to go down by 13 and leave me with 1. Up here in the A there were 28, but I've already placed 15 of them, so this number is going to come down by 15. Alright, and leave me with 13. And then this one here, I can see that I've already got 12 of them placed, so this is coming down to 8. And this is where I say don't walk away yet until you've added them up. Did you get 44 in total? And if you did, something's gone wrong. You shouldn't have. How many are missing, Jaden? There should be 5 missing. That 5 can be placed anywhere as long as they're not inside the circles. And there is a last one that Dave put up here. He likes to put some multiple choice up every now and then. And you don't have it in yours, but have a read. A group of 5 students from a band form a band. So I'll draw it for you. There's the band and there's 5 members in there. They're the universal set. All the members, except for the singer, can play either bass or drums. So all of them except the singer. So where will I put the singer in this particular Venn diagram? On the outside. There are 4 people still to place within the circles. So it says all band members except for the singer can play either bass or drums or both. 4 can play bass and 3 can play the drums. Alright, well I've got a problem. 4 can play bass, 4 play bass, and then it says 3 play drums. I've got 7 people, but I really don't have 7 people. I know I've only got 4 real people. So what have you just discovered about the intersecting part? If you've got what look like 7, but there were only a place for 4, it looks like 3 of them are sitting in the middle playing both. So go back and adjust, alright? That means that there's 1 on that side. Are there any just drummers? Are there any that play just drums? No, because there's my total. A 1 and a 3 and a 1 make a 5. What's the probability? Oh, sorry, it's not a probability, it's just a how many members can play drums only. And the answer will come up as 0 in that one. Okay? So we're about to pause. Okay? We are about to pause. We'll have a bit of a 5-minute break. So I'll start again at 10 past. And we've just got some contingency tables and then some probability trees. Righto. Contingency tables, probability trees. 5 minutes. 5 minutes there. You right? Oh, yes. Yeah. Yeah. Do they? Yeah. And again, if at the end of this lesson any of my tute wants to pick up their papers, all right, if any of my tute want to pick up their papers because they might have some time to work on their redemptions. Okay, I don't have a problem with that, working on their redemptions. Just trying to think. Hey, Jake, has he gone, like, that's all right, I was just wondering, I might just start then, because I think we're all, Casey, was there someone, oh, it's Jacqueline, that's who I'll wait for. Jacqueline's over there. I'll just wait another minute. Do we know yet where our exams are on yet? Has that info come out yet? Not yet? Yeah. Yeah, no, someone will probably inform me soon when we know. Justin, do we know where our exams are yet?
I don't think so.
Not yet? Must be coming soon. just reading the free lunch on Wednesday the 19th, 3 hours. Sounds like a good lunch, Rebecca? One of those stressless lunches. All right, we'll get started, guys. I think it's time to start. Down the bottom of page 142. We ready? We're about to get started and we're about to fly, hopefully, through these last batch of questions. Here we go. Shush, because if you miss this little bit, you won't see it and it's bound to be in one of your papers. If not this quiz, then it'll be in that final, if not both of them. Here's what we've got. Each example we've considered so far has involved the probability of a particular event when sampling from the entire sample space. Now, I've circled that entire because obviously that's about to tell me that something is about to change. Now consider the probability of an event where certain information about the event is already known. Now, what people think is that they'll see this coming, but mostly they don't see this coming. So you just have to get used to how the questions are worded, practice lots of them, and say, well, hang on. So sometimes I'm going to consider all of the sample space, true, but then there's going to be these conditions put on me where they've said certain information that you already know. So it won't be the entire sample space, but a subset of that. So here's what it's got. Down the bottom, this is for you to fill in. From a class of 20, so I'm going to put those 20 down here in the corner, like this. 10 played guitar, so I'll put my 10 on the guitar side. 14 played piano, and it tells me 6 played both. So I've put my 6 in the middle. Now obviously I've got more than 20, so I've got to do some adjusting. Take the 6 off the 10, leaves you with 4. Takes the 6 off the 14, leaves you with 8. Do a double check on yourselves. Does it add up to 20? I think I'm missing some. How many am I missing? As long as there's 2 floating around on the outside. Now we're ready to go. What's the probability of randomly selecting a student from the group of piano players who also plays guitar? So right there the word said you're not picking from all 20, but you are picking from the group of piano players. Now the group of piano players are just this group of 14. So I'm going to remind you, N, okay, for the piano group, the number in the piano group is 14. So that means that the probability I'm about to find, alright, I'm going to say who plays a guitar, but you also know that they already played the piano, is going to be out of 14. So the very first thing now, I'm changing what it's out of. So out of those 14 that play piano, how many play guitar? And the answer would be 6. The 6 that are sitting on the top. 6 on 14, and again I always show my original because then I'm going to simplify it, and I'm getting a 3 on 7. That looks like a pretty ugly decimal, so I'd try and avoid it. If only addressing the group of students who play piano and or guitar, what's the probability of selecting a pianist, it says. So second part of that question, whereabouts are we there? If only addressing the group of students who play piano and or guitar. So why are they telling me that? Is it still out of 20? Is it out of 14? Or is it out of another number? It's out of 18 because it said hands up if you play piano, hands up if you play guitar, or if you play both of them. So far what I've got is the number that I'm considering will be the number out of 18. So let me just put that the probability that I pick, okay, a pianist from, oh, this pen, try it again, and I'll say from, alright, that subgroup I'll put here, from the subgroup, means it's out of 18. So if you're only looking at anyone that is sitting in those 2 circles, like that, which is 18, how many can you see play piano? And I've got a 14. So this one is a 14 out of 18, which comes down to a 7 over a 9. So conditional, you won't see the word conditional, so you've got to be careful when you're reading your question that maybe we're not taking the whole sample space, but part of, okay? Now, contingency tables are also known as two-way tables. So there's a few of them here. They're pretty much complete, so if you've just got your calculator, you just have to do a bit of filling in. But they present data in a nice, easy fashion. So here's what I'll say. You've got that in a sample of 250 children, so straight away that's the total number. So that's the universal set. The universal set gets placed here because it should total from this side and it should total from that side. So the universal set is the 250 children. Now the words say 119 have been vaccinated, so find the row that says vaccinated, and it says 119, not in the first, not in the second, but in the total over here there should be 119 that are vaccinated. How can you tell me how many are not vaccinated? You already know the sample space down here is 250. I've just declared 119 are vaccinated. I don't need for them to tell me how many are not vaccinated because I can calculate 250, take away 119, should be left with, any numbers out there? 131. So don't wait for all the clues. Sometimes you've got to squeeze a clue, so I squeezed it out while I was there. 74 have contracted mumps, and 14 have been vaccinated against mumps and have contracted mumps. So hang on, let me read that again. 119 have been vaccinated against mumps, so we placed them in. 74 have contracted mumps, so contracted mumps, that's these ones down here. So I'm going to put the 74. If 74 have had mumps, straight away you can tell me how many didn't have mumps. How many are going to come up with? Anyone backing me on 176? And the last clue was that 14 have been vaccinated against mumps and have contracted mumps. Now where do we put that last clue? That last clue there goes where? In the contingency table. So there are 4 cells, if you think of it like cells. The 14 are up in the top left because they were told that they had mumps and they'd also been vaccinated, so it's where the two collided. Now we should be able to figure out the rest of the cells. So again, every column and every row you can see the totals. So start filling in the numbers that you don't have. I think this one is a 105 sitting on that position. I think this one down here should be a 71. And looking backwards, it looks like this one here is a 60. Now double check with yourself that all your columns and your rows add up, because again, you don't want to go forward if you've got the data wrong. And here come the questions that go with it. So you know you've got 250 students there, or 250 children there. You can start answering the questions. I'll just wait to see if you haven't filled them in. This is just coming up with all the numbers we just did. That's the completed table, and here come your questions. If one child is selected at random, determine the probability that the child has been vaccinated. So I'm just going to put probability that they're vaccinated out of 250. All right, how many from the total that have been vaccinated? Get your finger on the vaccinated, go right to the very end, and you'll get 119, which I don't think will simplify. Not contracted mumps, so no mumps, so I'll put here no mumps will be out of 250. Go to the column, go down to the no mumps total. We should have 176. That looks like it simplifies, so it comes down to a 88 on 125. Next one says been vaccinated and contracted, so they were vaccinated and they contracted mumps. I'd say that's the 14 sitting in there. So 14 out of 250. And again, it looks like it's going to simplify. And I'm getting a 7 over 125. And then it's got not been vaccinated, so I'm thinking about these not being there, and contracted the mumps. So it looks like I'm talking about those guys there. So not vaccinated, but they got mumps. It looks like there's a 60 out of 250. And a 60 out of a 250 comes down as its best, 6 on 25. And we're done with the contingency table. Now your job on the next one is to fill the info in. So if you've started reading, all right. Now I've just put the numbers in to start us off, so you can go with that as well. A company has extensive health club facilities available to its employees. Records for last year indicate that of 210, there's our universal set, 210 employees, 90 used the facilities at some time. So 90 used the facilities, that's where the 90 would have come in. Of 170 male employees, 65 used the facilities. So that's 65 used the facilities that were male. Now the rest of those numbers will fill in. So get them all in there. And then there are a couple down the bottom, and we'll pause on the last one. So make sure you've filled in all the numbers from their clues. If one employee is selected at random, determine the probability that the employee is male. So this is the probability that I pick someone that is male, and I'm going to go for the total of that column, and I'm going to put it over 210. There were 170 males. I'm going to guess that goes to 17 on 21. Second one says that they're female and did not use the health club. So females are these, and did not use would be these ones right there. So I think it's a 15 out of probability that they were female and not a member or not using it. It was 15 out of 210. Somehow must simplify. A 1 on 14. And the last one to be careful of, and again it's just gone to a new page, but it's the last one on your page 143. It says with a condition. So the question says something like, determine the probability that a person chosen used the health club. And what the problem is if you don't listen out to the last part, you jump straight away. You actually stop reading, that's when you'll be in trouble. Because if you stop reading, you can see that, you know, that 90 used the health club, and you would have thought 90 out of 210. So this is what most people want to give us, 90 out of 210. But it said determine the probability that a person chosen used the health club given that a female was chosen. So we're only going to look at those people right there. So conditional probability often has you zooming in on a group and blocking everybody else out. So this now says, because you know that you are only looking at the females, then the number in that group is 40. So the probability that I pick someone, okay, who uses the health club, I'll put here that is health club, and I'll say but female, they had to be female, is now a probability out of 40. Out of the 40 females that we had, how many actually used the health club? The answer is 25. So a 25 on a 40, divide by 5s, you get 5 on 8, which is a very different answer to that one up there, the 90 on the 210, which is what most people want to do. So this is just, again, you can look it up on the slides, just another question thrown in. There was nothing really much there. You've got another contingency table. All I'll say is when it comes to these tables, they love to put questions about testing, all right? So I'm just going to read through this one because it's more just how you get caught on the words. A blood test is used to diagnose TB. When the results of the blood test are positive, it indicates that the patient has TB. So here I see blood test positive. They're the people that have TB. When the results of the blood test are negative, it indicates that the patient does not. So the test says these people have it. The test says these people don't have it. However, when you look at the other side, if we now know, not the testing, but we actually know the people, the patients, who has it and who doesn't have it, all right? So, in fact, the blood tests show that 468 have it, but over here, there's only 460 patients who have TB. Now, we've got a problem with that So when you read these questions, the question that goes with this one, okay, underneath says, how many patients were correctly diagnosed by the test to have TB? All right, how many patients were correctly diagnosed? So that means you stop and think. The test had to say you have it, and you actually do have it. So what number can you see on the grid are those people? Anyone want to call it out? 454. 454 is the response to, that tells me that you are both, the test says you have it, as well as you actually do have it. So these are the 454 people who were correctly diagnosed. Now, even in that sound of that question, if they were correctly diagnosed, what's the problem with this? There are some people on there who were not told, or perhaps the test said that they had TB, but they actually didn't. That's this group of people right there. So we have a problem with our tests, and that's where when somebody puts a trial into the marketplace, they want to make sure that their tests don't do, all right, what this is doing. This is telling 14 people that they have TB when in fact they don't have TB. So another problem we get is the reverse, I guess. In what percentage of the blood tests for TB were the results of the blood test incorrect? Now you've got to think about this carefully. Where was the testing incorrect? Now I've got an asterisk on one position. There's a position there that the blood test said you have it, but 14 people knew they didn't have it. So that's an incorrect reading. Is there another incorrect reading? And which number's that? The 6 people right there. So what's happened is those two with the asterisks on them, they're the results of people. Their blood tests have said one thing, but in fact in reality it was not that at all. So what percentage of the blood tests for TB, so what percentage, to get a percentage, so I don't know why I went that way, but my hand wants to go that way. What percentage, so before I get a percentage I tend to make a fraction. How many out of the 600, all right, were the results of the blood test incorrect? Well, there was the 14 who the test said you have it, but they didn't. And then there were the 6 that the blood test said you don't have it, but they did. So I've got myself 20 out of 600. So please make a percentage up out of that. What kind of percentage do you get? How will I put it up? I'm getting a 3 1/3%. Now again, when people do these trials, okay, for new drugs or new tests for certain things, you want to make sure that that percentage is low, because it's no good making people sit through a test if it doesn't actually give them the right results that they're hoping for. So that's what they keep an eye out for. So again, I'll put that through the slide and then I'll get to the tree diagrams. Now we're about to get some simple tree diagrams, so listen up because we're going to sort of zoom through the easy ones. Tree diagrams and tables can be used to represent the possible outcomes from independent events. 2 events are independent if the occurrence of the first has no influence on the occurrence of the second. For example, a coin is tossed. They can either put it in a table so you can see that there are 4 results, or you can put it into a tree diagram. Now, the main thing about a tree diagram, the reason why most people don't get this right, is because they forget to say what they're doing up here, because they forget and get lost in the question. I'm tossing a coin twice. So what I do is the first time I put first toss and I say I can get a head or a tail. Second toss, I do it again and I can get a head or a tail, and it doesn't matter what my first result was. Okay? The outcomes, there are 4 of them listed. If you do it this way, these are equally likely. That just means there are 4 outcomes and each of them has a 1 in 4 chance of happening. Okay? So what's the probability of getting a head and a tail? Now it doesn't say in any particular order, a head and a tail, a head and a tail. So the probability of a head and a tail in any order is 2 out of the 4 outcomes, which is 1 out of 2. Okay? What's the probability of getting a head then a tail? So now the order is definite. So a head and then the tail, and I can see that only happens once out of the 4. So the language is the part that's going to hurt the most in this particular zone. When it comes to coin and rolling the dice, okay, it's got here the table, and again you can go through the table or you can do a tree diagram. There's the die. It doesn't actually matter which one you do first, so it wouldn't have mattered if you did the coin first, alright, but the outcomes are listed and there are 12 outcomes. So what's the probability of getting an even number and a head? So the probability will be out of 12. Count up how many are even, as well as having the head. 1 there, 2 and a 3. I'm only getting 3, so I've got myself a quarter. Okay. Now this one here, up on yours, you've actually got the grid with all of the dice. Alright, so the grid didn't come up here, so you guys are looking at it, and there are 3 questions. So how many are in the sample space? First thing I'll do is put the sample space here, and there are 36. So can you see dice 1 across the top and dice 2 going down? 6 by 6 grid gives you 36. Now I get asked a lot, we all do, we get asked about, should I draw all of that? Well, you've got a resource sheet. And for next week's quiz, why wouldn't you draw it? Because if there is a certain question on it, you've got the grid ready to go. Okay? So what's the probability of rolling a total of 3? So if that's the game we want, the probability out of 36, how many ways can you get a total of? So you keep doing that while I plug this in. How many ways can you get that? Keep answering all of them for me, guys, just so that I can plug this in. Because PowerPoint's further away than I want it. Keep putting them all in. Keep putting it all in. What kind of answers, Rebecca? What do you get for the total of? Total of 3. 2 out of 36, which comes down to 1 on 18. Is that right? Justin, what do you get for the probability of rolling 2 3s out of 36, Justin?
2 3s.
Yep. 1 out of 36. What's the probability of rolling a total of 7? Anyone counted them up? Total of 7, anybody? 6 out of 36, which turns out to be a 1 out of 6. All right. So again, make sure you've got that down, all right, on your resource sheet. The product rule. Here's what happens. We're about to draw some tree diagrams, but we just did a tree diagram, or the book had it done, where there were 12 outcomes. Now the thing is, if you look at the bottom of page 144, that tree diagram is great. It gave us 12 outcomes, but we don't want to keep drawing the tree when the number of outcomes gets too large. And the way we can save ourselves is we put probabilities along each of the branches. So this is what we need to know. If we're going to put probabilities along each of the branches, then we better know that you can do this multiplication, or this product rule. It means it's going to be the product of event A and event B, all right, occurring, it says either in succession or simultaneously. So what happens is, when you're going to go up with this, what's the probability of getting a head and a 3 when tossing a coin and rolling a die? So what you can put along here, you guys have got a bit of a space in there. Let's have a look. It's not much. I'm not drawing a huge tree. All I want to know is if it's going to get a head or a tail, I'm going to put a 1 on 2 and a 1 on 2, because it's got a half and a half chance. And the die, and all I'm interested in is rolling a 3. So what I'm going to do is put, it'll either be a 3 or not a 3, and this one here will either be a 3 or not 3. Now I actually don't need all of that table. The only one I want is the one that goes across from the head and then rolling a 3. Rolling a 3 is 1 out of 6, and this is 5 out of 6. Now I want that outcome. The probability of getting a head and a 3 would be a half multiplied by a 6, and that gives me a 12th. And that's how you can get it without having to draw all of the outcomes, because it's going to get too big. Have a think of this one, the probability of getting 5 heads when tossing 5 coins. Now think about what I just started with. So I had that this was a head and this was a tail. Now I'll just get started. There's the first coin, there's the second coin, there's the third coin, there's the fourth coin, and there's the 5th coin. Now I'm not going to draw the rest of that tree in, because I can see that I don't really need the rest of that tree, because all I got asked was what's the probability of getting the 5 heads when tossing the 5 coins. And each of these would have a half on them. Now, anyone that wants to tell me it's 5 halves gets you 2.5. It's bigger than 1, so it can't be 5 halves. What's it going to be, Jack? It's not 5 times a half, but it's a half to the power of 5, which is otherwise known as 1 on 32, I hope. Just check on me. 1 on 32. What's the probability of getting 3, and it's just being termed as A, B, C, D multiple choice questions correct. That means you've got 4 things you could have picked from, an A, a B, a C or a D. 1 of those is right, 3 of them are wrong. So if you think about it, you can either be correct, and I'll put not correct. For you to be correct, it's a 1 in 4 chance. Alright? That's first question you had. Second question, you could have been correct or not correct. Third time, you could have been correct or not. Now you just want the correct, correct, correct. So that's a 1 in 4 times by a 1 in 4 times by a 1 in 4. Oh. A 1 in 4 times by a 1 in 4. So again, it's not 3 lots of those. The probability of 3 correct is going to be 1/4 to the power of 3. Answer to that one, anyone? 1 on 64, I hope. 1 on 64. Now the crucial bits we have to fly through here are down the bottom. And in words you might think, oh, I don't quite get it when it says it in words, but they're important little statements at the bottom of page 145. Each segment in a tree is one stage of a problem, and the probabilities on those branches from each point must sum to 1. This is where your complementary work is really, really important. They must add up to 1. To calculate the probability of reaching the end of any complete path, you have to multiply to get to the end. So think about it. You multiply to get to the end of a branch. And if you want one outcome plus another outcome along a tree, then what you have to do is multiply to get to the end and then add their probabilities together. Alright, so we're going to do quite a few here. Here's the first one, guys. I think it's on the top of page 146. It's already got it worked. You've got a family of 2 kids. There are the probabilities, and what I want you to check, it says that every time you come from a point, the sum of the probabilities should equal 1. Every time you come from a point, the probability should equal 1. So that's what we're looking for. Alright, those little circles there. And then the question that goes with this, the probability of a boy and a girl, alright, wanted to be this one and this one. Both of those are the outcomes I'm looking for. To get to the end of this line here, then this one would have come up as, this one here would have been a half times a half. This one here is a half times a half. This is actually a 1/4 chance. This is a 1/4 chance, and we wanted both of those. So the 2 ticks get put together to get 2/4. Now the next one's got 3 coins, I think, being tossed, and there's a little bit of space there. List all the possible outcomes and determine the probability of obtaining 2 heads and 1 tail. So see the space you're in as best as you can. Alright, this is what you've got. You've got your first one, heads or tail. You've got the probabilities, alright, are a half and a half on that one. Put them all in. If you don't get time to write them all in, do that rest at home, but it wants you to list all of the outcomes, and all of the outcomes have been listed on the side. So these are in order, head, 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 then head, head, tail, and so on, all the way down. There are 8 outcomes, but you can see why a tree diagram doesn't want to be used when there's too many outcomes. It's going to get too crowded. And the question wants you to figure out, alright, what's the probability of getting, it says all heads. That would have been this result. Now we'll go with the half times the half times the half, which is just travelling along the branches, which is a 1 in 8 chance. a tail and then 2 heads. So for that to happen, you think about a tail and 2 heads, that's this result or this outcome. Again, it's a half times a half times a half, which is again a 1 in 8. And at the bottom, it's just prepping you for what's the probability of getting 4 heads if I toss a coin 4 times. So it's just getting you to think about, you don't really want to draw the tree diagram to it, but you know what it would look like. So think about the probability of getting 4 heads if you tossed a coin 4 times. A half times a half times a half times a half, which is also the same as a half to the power of 4, which is 1 on 16. Alright, this is the main part we want to get to. Page 147 has us with a tree diagram which says it has unequal probability. So this is where the questions, alright, start to depend on how good you can draw your tree. I choose 2 marbles from at random from a bag containing 5 blue and 3 yellow. So those clues there, 5 blue and 3 yellow, make a total of 8. So there's a total of 8 that I'm picking from. Find the probability of choosing 2 marbles if I replace. Now highlight that word because they're important words for you to catch in questions. If the first one gets looked at and then gets put back in the bag, it's going to make a difference to your answers. So here's the first thing that happens. First time I go to pick, 5 on 8 chance of getting a blue, or a 3 on 8 of getting a yellow. Do those 2 add up to 1? That's what your eyes need to keep seeing, and that's why you don't write them down as decimals. They're much easier to work with as fractions. So second time round, you've put it back in, so it hasn't changed the probabilities. These 2 here add up to 1, as do these 2 here. And the question then said, find the probability of choosing 2 blue out of all of that. Now here's the problem. If people think there's a 1 in 4 chance, that's where they're going to get it wrong, because it's not equally likely. So put down on there somewhere, these are not equally likely. So you don't go 1 in 4, get sucked into that. What you want to do instead is look for the BB and run your finger along the branches. 5 on 8 times 5 on 8, which is 25 on 64. Second time round, it's going to be done again. But this time, alright, you are going to be putting it back, sorry, you're not going to be putting it back in. I do not replace. Alright, so because you're not replacing, see the little space you've got in there? Our job is to draw our tree diagram. So the first time round, we're going to get a blue or a yellow. So the first time it's still a 5 in 8 and a 3 in 8. Now here's where I'll do a bit of a pause and say, whatever I've taken out of the bag the first time now is affecting the next batch of numbers I work with. So it all depends on you being able to play a game. First of all, pretend you've got the blue in your hand. If you've got the blue in your hand, you've only got 7 marbles left in the bag. So I've put the 7s there so I don't forget. I'm holding a blue one in my hand. So how many have I still got that are blue inside the bag? 4. How many that are yellow? 3. Do they add up to 1? Because they should. Now if you're playing this game, you've got to start the sentence again, but this time say, but I'm holding the yellow in my hand. So I start the game again. If I'm holding the yellow in my hand, they're still out of 7, but I've got a yellow in my hand, so it's the yellow that has gone down and the blues are still at a 5. Do they add up to 1? So once I'm happy, now I'll say the probability of choosing 2 blue is this one. The probability of choosing 2 blue will be a 5 on an 8 times by a 4 on a 7. That comes out to be a 20 on a 56, which looks like it could have cancelled, so it's about a 5 on, I think, a 14. Something like that. Now that's going to make a big difference to your answers, okay? So read the questions carefully. You might not see the I do not replace. The words might not be that obvious. You've just got to be careful. This one here, I'll just set it up. It's that middle space there. It just says a probability experiment has 4 possible outcomes. So what's about to happen is it could be A or B or C or D. The outcome for A is 4 times as likely as each of the 3 remaining. So this, and this have all got the same probability. So I'm just going to give them a number called X. That is their probability. And A has got 4 times as likely. It is 4 times more likely, so it gets a 4X. What do I know the sum always has to be? What do I know the sum always has to be? And I hear a 1. This is called making an equation, guys. 7x is equal to 1. X is equal to 1 on 7. That's actually not the question. It's part way. Find the probability of A happening. A's probability was not X but 4X. So that's a 4 on 7 chance of happening. This is the probability of A occurring. Okay? So something like that could get thrown at you, where you've got to use a little bit more of an idea of equations and reading abilities. Down the bottom there, this one here's got the 20 tickets being sold in a raffle, and there are 2 prizes. What tends to happen is people forget how to take this in steps. So this is the first prize. I can either win the first prize, and I'll just put not win like that. If I've got 5 tickets in my hand, then I've got a 5 in 20 chance of winning, and a 15 in 20 of losing. Now I don't simplify those, because when I go to do the next prize, it's easier just to work with the 20 coming down to a 19. So when I go to find my second prize winner, it all depends on what happened, okay, in the first. So here's what I've got. I play the story twice. The first time I play it, I won. So there are now only 19 tickets still in the hat. If I won, then one of my 5 has already been taken out. So I've only got 4 tickets that I can win with, and there are 15 in there that are not mine. Does it add up to 1? Then play the whole story again. But remember, the second time you play the story, you didn't win. So it's out of 19, sure. But you've still got 5 of your tickets still able to win. So you've got a 5 in 19, and this one has come up as a 14 on 19. Check that they add up to 1. What's the probability that I win 2 prizes? That's this one up here. So the probability that you win 2 prizes will be a 5 on 20 times by a 4 on 19. So I'll let you figure that. All right. Does it come down to, I think, a 1 on 19? Do check on me. Yeah? And then we've got the last page for us is the at least. This is just going to show you a bit of a shortcut that can happen. It basically says, all right, that when you see an at least or an at most, I'm saying that mostly, yes, there will be a shortcut way of getting it. See down the bottom of that question we just dealt with, it had what's the probability of winning first prize, and then it had what's the probability of winning at least 1 prize. So that at least, okay, would have meant that on my tree diagram I wanted a W on there once or twice. Okay, so what it does is it lets you say there is a shortcut way of finding that out. So I'll go on to the next one so you can see it a bit clearer. And at least 1 is usually the probability, okay, of, and we go to this one here, of the 1 minus, okay, the probability that none happened. So it's usually that you've actually got a situation where, for this example, is this one drawn for you guys? So back on that other one where we had done for 3 coins being tossed, if it was being asked what's the probability of getting an at least 1 head, what that wants you to do is say, I notice that I want anything with 1 H or 2 H's, 1 H or 2 H's, all the way up. Now you see how there are 8 outcomes and I've ticked 7? Because your job is either figure out all of the 7 outcomes probability, or the other shortcut, is do the one take away, the one you didn't count. So the probability that an at least, okay, 1 head, all right, will be 1 minus the probability that there were no heads, which means it's 1 minus, no heads meant the tail, tail, tail. So this would have been, okay, a 7 on 8. Now these were equally likely sort of trees, so we want one that isn't. So I'll go closer to this one. What's the probability of getting? This is where there was a typo. So see how the second one sounds on yours, on your page 148. It looks like it says exactly the same thing, but you guys have to change it to getting at most one tail. So at most one tail. All right, that means at most, all right, I want one tail. There is at most one, at most one. All right, that one's got two, so I don't want to tick it. At most one, that's got two, that's got two. How about the three? Way too much. The only one I'm curious about is that one. Will I tick the three heads? Yeah, because it hasn't gone over the tail qualifications, I guess. It's got 0 tails, so that still counts. So there'd be 4 there that you would want. So the probability of this would be 4 out of 8, which is again 1 on 2. So the at least, at most, be very cautious about them. I won't worry about this birthday problem, okay, because it was just thrown in there. This one here, you guys have got about the cards, all right, and it's just being careful to say without the replacement. Find the probability that both cards are black. First time round, you go and pick a black, and it'll be a 13 out of a 52. But if you've already picked one of them being black, then... Oh, my apologies, it is 2. Thanks, Rebecca. 26 out of 52. If you've picked a black, then this one's come down. The total's come down by 1, so it's out of 51. And you're holding a black in your hand, so this one comes out to 25. Now, I'll just leave that as that. You can simplify that. All right? The second part of that question, the cards are different colours. All right? So the first thing you want to do is you want to say... if they're different colours, so the first question over here, they were both black, okay? I'm just going to put that in because I need that answer there. 26 on... It's 25 over 102 if they're both black, okay? Now the thing is, I just wanted that one because see how this one says the cards are different colours? Well, they're either the same or they're different. So there's a couple of things you could do. For the cards are different colours, you could just do a 1 minus, all right, because they're either the same or they're different. So see this answer back here where they were both black? So that's the chance of them being both black. What's the chance of them being both red? I'd imagine it's just the same. Both red would be a 25 out of 102. So there's a 25 out of 102 that they're both black, a 25 out of 102 that they're both red. All the other options, they must be different colours. All the other options, they must be different colours. So I'm just going to put in here, the cards are different colours. I'm going to do a 1 minus the probability that they were the same colour. And the same colour we just did a moment ago. We did both of them being black and both of them being red. Okay, so that was the 25 on 102. And we wanted that taken away twice. Both red, both black. Does that give us about 52 on 102? And that probably simplifies to what sort of number? Is it a big one? Yeah, 26 on? Yeah? 26 on 51. Yeah, and that one there comes down to? What's it come down to? 13. On? 51. And our answer comes down to? Same thing? 9. What's ours coming down to? 26 on 51. You know what? Can anyone see? Our answer is 26 on 51. Rebecca's answer is 13. Can anyone see it? Good thing about when people make errors, just like when you guys make errors and I have to try and figure out what happened. She's not far. I mean, she's not the right answer, but she's not far. Can anyone help us see why that's not completed yet? She's got a 26 on 52. This is Rebecca's thinking, times by 26 on 51. When you do that, Rebecca, what you've said in your brain is I'll pick a red and then I'll pick a black. And then you have to go, and then you go the other side. So that's why your answer is times by 2. Okay? Now, I'll just leave it there because there's going to be someone coming in. There's the guy usually coming in. So you can see there it says a couple of more questions to do with the cards, and then there's a worked example at the bottom, okay? But if anybody from my tute wants to pick up, you're most welcome to pick up if you think you've got some time to work on redemptions. I'm just giving people, if they're planning their week out, they might just say, I've got some time. Anybody wants? Nicholas, I've got yours as well. You know how you sat with Dave. So I've got that if you want to work on it. Okay, not a problem. See you, Nathan. All good, Justin?
I'm great.
Fantastic. Yeah, let's
Crazy, isn't it? Yes. I think the next assignment would be for you to find a proper controller for this nonlinear type of behavior of the weather. Can you do that? Pardon? I think the next assignment would be to design a proper controller to stabilize the weather profile. I'm wondering whether you can do that.